Yeah, so uh, all you missed was that we are talking about state machines and vision today. Yeah, so a state machine is basically just like the fancy words for it is that it's like a mathematical computation model, which has a set number of states. And out of all the states, it can only be in exactly one of those states at a given time. And it'll change the state based on some given input. But really, like, it sounds kind of complicated, but they're super simple. Like, some real life examples are traffic lights or like a combination lock or something. So, like, with the traffic light, your three states are green, yellow, or red. And the input in this case is just the time, right? So you have a green light for, say, 45 seconds, you have a yellow light for 5 seconds, then you have a red light for 1 minute, and you just keep kind of cycling through those states. So at any given time, your light is only one of those three colors, and you know, like, that the parameter for like whether you're going to the next state is whether or not that whole time period has passed. And then the lock is also very similar. There's two states. It's either locked or unlocked. It can't be both at the same time, and it can't be, I mean, I guess it can be broken, but like really at any time you're only going to have locked or unlocked. And if you're in the locked state, you need to enter the correct combo to get to the unlocked state. But if you're in the unlocked state, you need to open the lock to get it back to the locked state or something like that. Um, yeah. Okay, this is really short. Any questions about that so far?
Nope.
Okay. So
Oh.
my first discussion question. Oh, you have a question?
Oh yeah, I was going to ask if like in terms of a robot, would it basically just be like a bunch of if-then statements, like checking
Yes.
for inputs
And
and whatnot?
yes, I will talk about that a little more in depth and like give some examples and stuff. But for now, I just want to make sure everyone understands like what exactly a state machine is, which is why I was hoping we could all kind of like go around and just like think of some more examples. Because like when you think about it, they're kind of like it's pretty common. We just don't tend to think about things in terms of state machines. So does anyone have an example they could think of?
Basically like any button with like digital input, it's either like pressed or not pressed.
Right. Yeah, that's a good example.
In that case, you could probably just apply any sort of video game controller or like a keyboard.
Mm-hmm. Yeah, definitely. A keyboard
Mm-hmm.
is like probably a more complex version of that since you have like so many buttons. But yeah, each individual button is always pressed or not pressed.
Also, like a TV remote to like turn it
Mm-hmm.
on and off.
Yeah.
An elevator with a bunch of pre-programmed heights.
Yep. I guess that one's definitely like a little more like the robotics examples we're gonna talk about, where like at any given time you're not necessarily on like the floor. Like you could be in between two floors, but your destination's always like one of the predetermined floors. Yeah, cool. So yeah, now we'll talk about some of it like more specific to robotics. So um, one of the main reasons why at least our team likes to use state machines in our programs is because it helps sync all of the different parts of a robot, right? Because it can always ensure that there are no conflicting instructions because there's only one possible state to be in. It can make sure that there's a logical progression of actions because you only go from one state to the other if a certain condition is true or if a certain action has been done. And you can definitely program it in such a way that all inputs and outputs are operating off of the same state machines. And so that really makes sure that everything is in sync. So WPI lib automatically actually uses a state machine to store the robot state. So whether you're disabled, enabled in auto, enabled in teleop, or enabled in test mode, you obviously you can only be one of those things at a time. And WPI lib makes sure that when that changes, you're running the right set of code that you've written for the specific robot. And then more specific to what we write, our team uses subsystem actions. So we have like each physical subsystem on the robot is associated with like a part of the code, and then this can respond to user input or sensor data to change the states. as Yusuf mentioned, it's very easy to program because it's just if-else statements to check for each subsystem, just to check what state we're in, and then just have the actions programmed there, as opposed to like having to check each time whether a certain condition has been met, like whether a sensor is triggered, whether a button's pressed. Everything is just right there with the state machine. And then we can use that to set target positions, like the elevator example that James gave, or do something more simple, like turning a motor on or off, setting a piston to forward or backwards, and just generally syncing all the actions across the subsystems. And I think another analogy that I like to use a lot for this is like, you know, when you're like in a mall and you have those giant maps like showing all the stores. So if you think that like each store is a state because you can only really be in one store at a time, and then on that map it'll show you the "you are here" like star, and that's kind of what the state machine is for the robot. It's showing it where specifically it is in this whole like in the whole sequence of events that it's doing, or like programmatically it's like this is where you are, whereas the map would show you physically where you are.
Yusuf, can you mute your mic?
Oh,
Thanks. Yeah, here I just have a like little graphic showing some of the systems that subsystem like states that we had this year. So everything was able to go back to idle mode, which was just like everything is um kind of no motors are running and everything's in like the relaxed position, I guess. And then you can go to intake mode. You can go to climbing mode, and also aiming and shooting. You can toggle between the two because once you aim, you can go directly to shoot. And yeah, so like we would have our single central state machine, which would be like have one of these set as a state at any given time, and then each subsystem would read from it and say, okay, if it's in idle mode, then I'm going to make sure that all of my motors are set to 0 speed. Let's say we're in aiming mode, then we're like, you know, turning our turret and trying to find the vision target. And then when we go to shooting mode, we turn on the flywheel and actually shoot. And some other uses that we've had is tracking, just generally tracking any other states. Like the game piece last year, we had an off-season bot which used the same like physical arms to pick up both the hatch and the cargo. So we would use a state machine, a very simple state machine that switched between either hatch mode or cargo mode, and just changing that one simple state machine would change the angle and the position of the intake. So it would either be folded in to pick up hatches or opened up to pick up cargo. It would set the rotation direction because we would have to rotate in opposite directions based on whether it was hatch or cargo, and determine how we're going to eject it because it's a different length of time to eject the cargo versus ejecting the hatch. Any other questions here? Okay. Are there any ideas for other possible robot states? None?
Like for 2020,
Yeah, sure.
like you need a state for if you have a control panel manipulator.
Yeah, that's the big one I was thinking of.
Oh yeah, and then for ours, I think we had like a different state for like either deploying or actually spinning the wheel.
Yeah.
I think our robot had a state in case we needed to like fix something on the fly. So like if we were trying to like fix our climber and reverse it, we'd have to have a different state for that altogether.
Oh, that's a really smart idea actually. And I think that's another really great example of how states can be like super flexible, because then you can make sure you turn off that state or have no way of getting to it when you're like actually in a competition.
Right.
Yeah. Any other thoughts?
I have a question. What if the robot is like doing multiple things at once? Like we had to have it moving the arm down and intaking at the same time for our intake?
Right. So in that case, you would make sure that you had a state which um both actions would be a part of the state. Like, yeah, we had a similar thing with our robot last year. We had an arm that would come down, and it also had wheels that had to spin. So we made sure that, like, for the spinning wheels, they would check if we're in intake mode, and then they would start spinning if we were in intake mode. And the arm would on its own also check if we were in intake mode, and then it would change the set position of it, right? So yeah, that's again another big benefit of using the state machine is that you just change it in one place, and then you can have it affect multiple
Mhm.
like motors or subsystems or however you have that organized.
Thank you.
Okay, are we ready to move on to the vision part of this?
Yeah.
Right. So in FRC, we generally use vision processing to like identify targets. Like the image there was for 2019 when we had the two-angled tape to show where um, the whatever the cargo bay was. And then this year there was the big like half or three-quarter trapezoid to show where the outer port was. And this is like a pretty common theme in FRC using the retroflective tape, which is really helpful because they make it in a distinct shape, which you're not likely to see in other parts of the field. And it also shines the light directly back in the direction that you shine light at it. So we typically use green light because it's not used anywhere else on the field. And so from the camera's point of view, it sees a lot of things, but whenever it sees the retroflective tape, the green light is reflected right back at it. So it's very bright. I think like if you ever try like putting yourself at eye level with one of the like vision cameras with green LEDs, like it's very bright if you're looking at the retroflective tape from there. And so, yeah, there's a few different like camera setups for that. I know our team uses a limelight, but and other teams might use like their own custom things like processors with a camera, their own software, and an LED ring. And essentially, I do the same thing. It's really based on like your team's budget. And typically, the data is sent over the radio and put into network tables, which you can then have an object in your code which reads from the network table to get a bunch of values, which I'll talk about in a second. So when you initially get the picture, like I said, this is what the raw picture looks like over here. It just, you see everything, but there's also the really bright green reflection. And so we can do a series of like thresholding, kind of like putting filters over that image so that all that's left is a black and white picture with just the green parts left. And like this diagram here shows, a lot of it is with the hue, saturation, and value filtering, because this slice right here with the green is kind of all we need, right? All the other colors, like all of this is kind of like the mess, that's everything else, but this little sliver of green is all we want. And so we can use like different filters on the image to just get that. Um, there's also like a whole bunch of other things you can threshold, like you can group nearby pixels so that if there's like in this image here, you can see there's like random flashes of green just from how bright the camera is, or the LEDs, not the camera. But the reflection, like on the plexiglass or something, it'll only be a few pixels, and so you can group the nearby pixels, which will make sure that these just random like speckles won't be in your final thresholding. And you can also do it based on size or shape. Again, they make sure that the vision targets are really distinctive in shape. Like if you have random plexiglass reflection, it's a very low probability that it'll be two lines like that. And so that makes it easy to kind of, filter out for a specific size or shape. You can kind of find like the contour. So this is here, like boxing it based on the contours. And there's also skew. So if you look closely here, there's there's actually two rectangles. There's a yellow rectangle and there's a blue rectangle. and this is a limelight output, I think, so it shows like that there's kind of an angle. If you were looking at the target straight on, it would be the two squares would be equal, but they use different things to make those two squares. So if the two rectangles aren't equal, your robot can kind of figure out that it's not like head on with the target. So I know it sounds a little weird, but it all boils down to like these little like tricks of numbers, which you can end up using in your code to figure out where your robot is. So just another few things about pipelines, is that you can save specific scales for each filter, because in different lighting conditions, things will be different. Like your workshop might be more dim than the actual competition field. So you kind of like, you have a range to work with, first of all, but also I would suggest like retuning when you go to competition, just to make sure that you're not picking up like other noise because of the way the pipeline has been tuned. And generally, you're going to start by adjusting the color thresholding, because like I said, the green is not very prevalent in the field. So just filtering out the green should get you most of the way there. And then changing things like the size or area or the width height ratio will help you pick out exactly where the target is. And yeah, there's just a quick like GIF here to show how like changing different values. So I think that's the hue probably, and it's only picking up the target now, and then you can kind of find the exact thresholding values where the target's reflection will be. And so you have this very narrow range of values, and that helps you filter out just those bright green spots there. So now that you have like this vision, like the target picked, and you're getting the values back to your computer, you can use vision to like do a whole bunch of things. So it can help, in general, it helps intake or place game pieces precisely and quickly, because the tape will normally be either where you're picking up your pieces or where you're dropping them off. And you can either adjust your drive train or a specific subsystem based on the input. And we'll talk about PID in a later lesson, but it's basically just a controller that helps you like move to a certain value. And a lot of applications are just simple PID. So like if you want to drive forward until the target is a certain size, you just keep driving until the target hits your specific value, and then you tell the robot to stop and eject because you know that you're close enough. Or another thing is you can turn until your target is centered and then shoot. So you can either turn your drivetrain, or this year we, for example, had a turret on our robot. So we just turned the turret until the target was centered and then shot our power cells. And then another example of something that we've done is automatically driving forward to get the intake. So we did it for the hatch panels last year. And so we would just put it into vision mode, and it would drive forward, and it would keep adjusting its course on the drivetrain using the target to keep itself centered. There's also like some more complicated things. So like this year, we had a hood on our turret, and we wanted to know like if we figured out how far our robot was from the power port, then we could know what angle we needed to put the hood at. So this looks a little complicated, but it's just basic trig. Once you know the angle that your camera is set up at, and the limelight or your camera will return the angle that it sees the target at. And so you add these two together to get this angle right here. You also know the height that you've placed your camera at on the robot, and you know the height that the vision target is on the power port. And so you can kind of like make this triangle here and use trig to figure out D and like the specific equations down here. Yeah, so it ends up being very simple. You just divide the difference in heights by the tangent of the combined angle. Okay, any questions? I think that's all I have, so.